Okay. Okay, so when they're talking about a geometric sequence and we don't know the terms, but they're telling us the product of the first three terms and the sum of the first three terms, we can look at what we'd get. So your first term, you're generally talking about a. Your second term, it's a r. And your third term is a r squared. But that gets a little bit complicated, okay? So what we tend to do is take, what would the term before a be? If I'm multiplying by r for each consecutive term, what would the term before a be? It would be a over r. And then a, and then a r. Are you with me? So when you're getting questions like this, you need to learn that this is what you start with, because if you start with this, it just gets too messy. Okay? So we're going to take the first term as a over r, we're going to take the second term as a, and we're going to take the third term as a r. So you need to learn that that's what you start with when you have these kind of ones, because then it makes it nicer, because it says the product of the first three terms. So if I multiply these together, it becomes, these cancel, a cubed, which is equal to 216. So straight away I can get a, because a is the cubed root then. Otherwise we end up with a's and r's everywhere, and it's awkward. So that's 6. So a is 6. And then it says the sum of them is 21. So now we know the a. So 6 over r plus 6 plus 6 times r is equal to 21. We have an r under the line. How do we get rid of something under the line? We're going to multiply across by r. So, and then put everything together. So to factorize it then, what do 6 and 15 have in common? They have 3. And then factorizing. If you can't manage to factorize it, you can use minus b. Two and 1 minus and minus. Perfect. So 2r is equal to 1, so r is equal to 1 over 2, or r is equal to 2. And then given that the common ratio r is less than 1, so this is our answer. We don't take that one. Okay. What were we trying to find? Find the first three terms of the sequence. So a is 6, r is equal to a half, so 3, and then 1.5. Because it said in the question, given that the common ratio is less than 1. Okay. To get what?
The three terms of the index.
No, so we knew that a was 6.
Okay.
And then we found r. So I'm just using the fact that your next term is that multiplied by that and that multiplied by that. Okay. Next one then, find the number of terms in the geometric sequence 81, 27, 9. So 27 over 81 is R, which is a third, is it? Yeah. Okay. My A is 81, my R is a third. Find the number of terms in the sequence. So my Tn is equal to Arn minus 1. So my Tn is 81, a third to the power of n minus 1. Now, the last term is 1 over 27, so we're going to say what n gives me that. So I'm going to bring across the 81. Sorry, no. Okay, so dividing by 81, I don't want means which way do you do when you're dividing two fractions? Do you do it like this and top middle by middle? Yeah. So it's going to be 1 over 27 by 81. Now, over here, this is the same as, can you see where I am? Yeah. 1 to the power of anything is just 1, so I can bring the power underneath to be with the 3. Alright, and we can ignore the top then. When we have an unknown in the power, our way of solving it is to write these to the same base number. We know 27 is 3 to the power of 3, don't we? And we know 81 is 3 to the power of 4. So our rules for indices say we add those powers. Alright, so we can just ignore the top, take the powers. Now you could solve it using turning it into logs either. So n is 8. I thought the calculator might give it to you nicer, but it doesn't, it just multiplies it out. And then if you multiplied it out, you'd be a while figuring out what power, but you get there. So if you didn't do this and you multiplied it out, I'll just do it so that you get 2187 equals 1 over 3 to the power of n minus 1. So from our logbooks, we can turn a power into a log. So we have the rule that says if I have 8 to the power of x equals y, I can change it to be the log of y to the base a is equal to x. So here's my answer, here's my base. So when we're trying to get a power down and we're taking a log, we normally take the base that's there. Okay, so then if you stick that in your calculator, you'll get the answer of 8 anyway. So then n is equal to 8. Alright, so you could do it that way either. Because they're the only two things we can do. If the thing we're looking for is up in the power, we either have to use logs or we have to write them to the same base number. Is that alright? Okay, so then we sometimes have exponential sequences. Exponential sequences are geometric sequences, But remember, exponential graphs are your graphs that grow really quickly. So it's to do with population growth, that kind of thing. And your x is in the power. That's what's different. So a ball is dropped from a height of 27 and loses 2/3 of its height on each bounce. So they don't normally tend to get us to get a TN or anything for these. They just get us to get values. Okay. So find the height of the ball on each of its first 4 bounces, hence write down the height of the ball after the 10th bounce, and after which bounce will the ball be at most 2.5 meters above the ground. Okay, so the first one, it's literally just starting with 27 and multiplying it by 2/3. And then starting with 18 and multiplying it by 2/3. And then starting, how many do we have to do? 4. Multiply it by 2/3. 8. And start with 8 and multiply it by 2/3. Oh, I read it wrong. Loses 2/3, so we're actually multiplying by 1/3. Sorry, that's my mistake. So it loses 2/3 of its height. So it's only 1/3 of 27 rather than 2/3. 9. Okay, so it loses 2/3 of its height, so it only comes back up to 1/3 of what the original height was. So 27 by 1/3 all the way down to 1 by 1/3. Hence write down the height of the ball after the 10th bounce. So we have to kind of get a general thing of what's going on. So this one was 27 by 1/3 by 1/3. This one was 27 by 1/3 by 1/3 by 1/3. And this one was 27 by 1/3 by 1/3 by 1/3 by 1/3. So on the first bounce we had 1/3, on the second bounce we had 2/3, on the third bounce we had 3/3, and on the fourth bounce we had 4/3. So a general equation would be 27 by 1/3 to the power of n, wouldn't it? Where n is your bounce number. Does that make sense? Yeah. So then the 10th one will just be 27 by 1/3 to the power of 10. And the answer is 1/2187. Okay, sorry. Didn't see what I'm doing. After which bounce will the ball be at most 2.5 meters? Okay, so we have our general formula, 27 by 1/3 to the power of n, and they want to know when will it be at most 2.5 meters above. So it's somewhere in between here anyway. So we're going to let it equal to 2.5 and just solve for n. So 1/3 to the power of n is equal to 2.5 over 27. Okay, so here we have an unknown in the power. We won't be able to write 5 over 54 as a power of 3, so we're going to convert this to logs. So log of 5 over 54 to the base of 1/3 will give us n. And there's the button on your calculator where you can enter a log to any base you want. So 2.16. Okay, after which bounce will the ball be at most 2.5 meters? So in between two bounces, so at 2 it'll be above it, after 2.16 it'll be below it. Alright? Okay. So now we're just going to look at sum of a geometric sequence again. It's just adding up the terms in the sequence. You have a formula from your logbooks. So the sum of n terms of a geometric sequence is given by that formula. Find T5 and S5 of the following. So we're talking about geometric sequences, so we just want the general term, and then to get T5 and then S5.
So do you use this formula instead because they're plus?
No, this is Sn. So we're still talking about geometric sequences, so this is the sum. The pluses don't mean that they're arithmetic. Alright, the pluses just means that they're added together. Alright, so we still are going to look and say, okay, like if I didn't know, if it didn't tell me, if this wasn't under geometric sequences, like if I'm adding it's plus 2 and if I'm adding again it's plus 6, so it's not arithmetic. Okay, so am I multiplying by something? If I multiply 1 by 3 I get 3, if I multiply 3 by 3 I get 9. So it's geometric. Okay, and remember my Tn for geometric is Arn minus 1, and then my Sn is this formula up here, but I first need to get my Tn. So A is 1 and R is 3. Okay, so I can drop the 1 really. Okay, so then T5 is 3 to the power of 5 minus 1, which is 3 to the power of 4 is 81. And then Sn is A 1 minus R to the n all over 1 minus R. So S5 is 1 times 1 minus 3 to the power of 5 all over 1 minus 3. Okay, and then the other one. So here, what am I multiplying by? A quarter, and yeah, so A is 1, R is a quarter, so Tn is 1 by a quarter to the power of n minus 1. So then T5 so 1 over 256, and then Sn so just be careful putting it in your calculator. So 3, 4, 1 over 256. Okay. We're nearly done now. So with both arithmetic and geometric, all you have is your Tn formula and your Sn formula. So you're going to be using one of them to get what you want. So this one is very similar to one we did earlier. In the geometric series, T3 is 32 and T6 is 4. Find A and R and hence find S8. So remember the one where we filled them in and we divided them by each other to get R and then A, and then like the only reason we need to do it is to find A and R so that we can do the S8. Will I do it? Yeah. Okay. So Tn, so we have our formula. So T3 is 32. So 32 is equal to AR power of 3 minus 1. So 32 is equal to AR squared. And then T6 is equal to 4. So 4 is equal to AR 6 minus 1. Which are the same numbers? Yeah. Okay, so then AR5 over AR2 will be equal to 4 over 32. So the A's cancel, I'm left with R cubed is equal to 1/8. R is equal to the cubed root of 1/8, which is a half. Okay, and then we fill it back in. AR squared is equal to 32. So a half squared is equal to 32. So A is equal to 32 divided by a quarter. So A is 8. Okay, and then that's all you need to get your Sn. We want S8. So Sn is equal to A 1 minus R to the power of n all over 1 minus R. And we have everything we know we need. So S8 is equal to A, which is 8, 1 minus a half to the power of 8 all over 1 minus a half. And just be careful putting it in your calculator. So the answer is 255. Sorry, I did something wrong there, I'd say, with the... Yes, I did. I didn't do that right. It's 128. Sorry. So 255 is the answer. See, they haven't put it in writing, so what we're going to do is go with what's on the paper. So 5 out of 6 and 3 out of 4, and if they put it in writing, we can recalculate when they come back. Okay, and we'll just count your best 3 and 4 and 2. Yeah. So it makes sense. So try 5 anyway out of section 1 and 3 out of section 2 if you can. Okay, so that's geometric. So then we're on to infinity. So there's only one formula, sum to infinity. So it just means for series that are getting smaller, they're going to go on forever. Okay? They're going to get smaller and smaller and smaller, but they're going to go on forever. So you're actually kind of able to sum them, because as they go on and on and on and on, they're so small that it doesn't really make that much difference. So find the sum to infinity of the geometric sequence. So again, it's just find your ratio. Okay, so my A is 16, my R is 3 over 4. So the sum to infinity, there's a formula in your logbooks. you're just filling it in. Now what we do use this for is writing a reoccurring decimal as a fraction. So we're going to do that and then we're done. Okay, so the sum to infinity of this series is 64. Alright, because the smaller the numbers get, they become minuscule and don't count too much.
So what does the 64 mean?
It means that when you add up all the series to infinity, it doesn't really go any bigger than 64. It's the sum of all the values. So what I think the 64 is that it gets closer and closer and closer to 64, but it's just that little tiny weeny bit short because of all the little fractions. Okay, so when we talk about our rational numbers, what's a rational number? Can anyone remember?
A fraction in the form a over b.
It can be written as a fraction, yeah. So this is what this is all about. So any decimal that has a pattern in it can be written as a fraction. If it doesn't have a pattern or doesn't terminate, what I mean by that is has a set number in its decimal places, then it's not a rational number, it can't be written as a fraction. So what we're doing here is actually writing decimals as rational numbers. So 2.3 means that this is recurring over and over. So the fraction is 2, 3, 2, 3, 2, 3, and it keeps going. Okay?
Why does or have to be less than 1?
Because to get the recurring fraction. Okay, so how we do this is we expand it just like I've done there, but then we split it up. So we put the first 2, 3, and then we say, okay, what would I need to add on to that to get the next 2, 3? What would I need to add on to that to get the next 2, 3? And so on. Okay? Now this goes on. Okay? So I split it up into whatever my pattern is. So the first 2, 3, and then I have to put in 2 zeros and 2, 3, and then 4 zeros and 2, 3. And then this is my series. This is my first term. And then I need to say, what did I do to here to get to here? So to find out, I do 0, 0, 2, 3 over 0.23. And the answer is 1 over 100. Okay, and then you use your sum to infinity formula. So A is 0.23 over 1 minus 1 over 100. And that's 23 over 99. So with these questions, it won't tell you that it's anything to do with sum to infinity. Okay? So write the recurring decimal as a fraction. You need to know that it's sum to infinity you use. The only thing I want to point out on that is different types of recurring fractions. Okay, 0.7 that would be 0.77777 and so on. 0.23, it's only the 3 that's repeating. This means that 3 is the start of the pattern and 0 is the end of the pattern, so it's 370. And here the 1 isn't repeating, but the 62 is. So be careful then when you're setting up your first term. You can let your first term be 0.2 and then see what you do to get 0.23.
Is there a way to put that into the pattern?
Not that I know of. Okay. Now quickly we're just going to run through kind of what you would have dealt with at junior cycle in patterns. So we would have done a quadratic, and now we're going to do a cubic, and it's straightforward enough. Okay, so linear we've talked about, or arithmetic. Quadratic then. So quadratic is when your second difference is constant. Okay? Okay, so my second difference is constant, it's quadratic, so then I know my quadratic formula is going to be an squared plus bn plus c. So it's just our quadratic, but instead of x's we have n's. A is equal to half the second difference. So you need to know that for a quadratic your a is half the second difference. So in this one my a is 2. And then I need to set up some simultaneous equations and solve them. Okay, so my t1 is 7. So 7 is equal to 2 times 1 squared plus b times 1 plus c. So 7 equals 2 plus b plus c. So b plus c is equal to 5. And then t2 is equal to 17. Okay, so quadratic equations, bring this one down and multiply by minus. So minus b minus c is equal to minus 5. So b is equal to 4. So then b plus c is equal to 5. 4 plus c is equal to 5. So c is equal to 1. So there you have your values. So tn is an squared plus bn plus c. So tn is equal to 2n squared plus 4n plus 1. Can I go back up, is it? Okay. So quadratic, your second difference is constant, and half your second difference is the value that goes in front of the n squared. And then you do quadratic equations using 2 more values. So t1 and t2 normally. Then we just need to look at cubic. So cubic, the third difference is constant.
Can you go back up to the time?
Yep. Yep. Okay, so cubic, the third difference is constant. Okay, so I'm just going to write this down here. Did I? Oh, it's -1. Oh, how annoying. Sorry. Everything else is right except for my first one, isn't it? Okay, so third difference, constant, means a cubic. Now your A is a sixth of the third difference. And your Tn is an cubed plus bn squared plus cn plus d. So in this question, the 6th of 12 is 2. Now, so we have cubic, so we have 3 unknowns, so we need to do 3 equations, so it's simultaneous equations like we did for the last one, but just you need to do 3 terms. Do you want me to do it, or are you happy enough? Do it, or happy? Happy. Okay, so you just fill in T1, T2, and T3, and solve 3 simultaneous equations. Okay, and you'll get your values then for your Tn. So there's just one more example I want to look at, and it's just drawing actually, what's this got to do with it? Probably another. Yeah, this is a quadratic, and all I really want to point to is if you have to draw a sequence, so I won't even go through the whole example. So this turns out to be a quadratic, but if you're asked to draw a pattern, start your drawing with the first one and add to it to get the second one, and then add to it to get the third one. And then once you get to doing the one you need to do, you'll know what to do. Alright? So that's just a bit of advice if you have to draw a pattern. Everyone happy with that? That's it.